So, we will continue our calculation. So, at higher temperatures, that means temperature is very high compared to Debye temperature theta d. Theta d is defined, right, theta d is defined. So, this theta d by T is very less than 1. So, our x is very less than 1. So, e to the power x equal to basically if x is small less than 1. So, one can write 1 plus x square. So, higher term one can neglect. So, 1 plus x minus 1. So, it is x. So, x cube by x. So, x square. So, I have to integrate x square dx over 0 to x d. Okay. So, then I got the x cube by x d cube by 3, x d cube by 3. So, x d is theta d by t. So, it is cube. Okay. And so, this part from here multiply with this. So, this will go and 3. So, it will 3 R T, it will be 3 R T, and this C V is del E by del T at constant V will get 3, will get 3 R. Okay. Now, at higher temperature, so this I do not need. Well, let us see at higher temperature. So, at lower temperature, that means T is very smaller than theta d. Okay. So, that means theta d by T is very smaller than this. So, this will be very greater than 1, this will be very greater than 1. Okay. This will be very greater than 1. So, e to the power x is very greater than 1, e to the power x. So, it is one can take neglect 1, one can neglect 1. So, this we can write, so I think I will delete it here. I will do. So, this part integrating part, what I will get? I will get x cube, okay, x cube and e to the power x dx okay. So, this way one can consider this, and other way I think it is a easier way one can do that. In this case x is this the theta d by t is very greater than 1, x is very greater than 1. So, theta d by t, okay, if t tends to very small temperature, it tends to 0, t tends to 0. So, this will be infinity. So, this integration we can write 0 to infinity, then x cube e to the power x minus 1 dx. This integration you have ready made solution of this. So, this basically is pi to the power 4 divided by 15, okay, pi to the power 4 divided by 15. So, it is so from so this way one can, since it is ready made, it is available. So, just we took that opportunity. Otherwise, as I was trying to find out that it is a very greater than 1. So, one can neglect 1, okay, just x cube e to the power e to the power x dx. So, one can integrate also, you can find this same result. Okay. So, what I am getting? So, basically I am getting here integration value is giving. So, my total energy E now, my total energy in this case E now. So, this the integration part giving this value, and then I have 9 R T, 9 R T, and then T by theta d, T by theta d cube into this. So, that is the total energy at very low temperature, right. So, now you can find out the CV equal to del E by del V del T at constant V, okay, equal to. So, this basically T to the power 4. So, if I differentiate it, it will give me 4 T cube, 4 T cube. So, it will give me 4 T cube. So, 4 into 9. So, that is basically 36 by 15, this 15, 36 by 15. So, T cube R T cube by theta d to the power 4 by theta d to the power 4, because no theta d by cube, okay. So, then I can write the same way, because this absorbed by this differentiation. So, T by theta d cube, okay. So, I think this the and this the 3, okay. So, this I can write 12 by 5 basically, 36 by 15 means 12 by 5, 12 by 5 I can write, okay. So, here CV, now you can clearly see CV is proportional to T cube, CV is proportional to T cube. That is the great success of Debye theory, that experimental result demands the variation of CV at low temperature as a T cube, okay. CV varies as a T cube means CV proportional to T cube, CV proportional to T cube. So, that is the experimental result demand, and from Debye theory successfully we could derive this dependence of CV on T as a proportional to T cube. So, that is the great success of Debye theory, which explain this whole this behavior of CV, whole behavior of the CV. So, I think I do not need them now. So, at low temperature CV we got 9 R no 12 by 5 what is the pi to the power 4 will be there, here pi to the power 4 will be there, yes. So, these are pi to the power 4 R by, okay, theta d cube, then T cube, okay. So, now this CV curve is basically that CV curve, I think I can delete them. So, CV curve for I have shown you earlier as a function of temperature, this is CV. So its variation is like this, I think it's not like this, it's more sharp here. Okay. So, this is the value, this is 3R value at higher temperature. So, this temperature generally Debye temperature theta d, and at lower temperature is very less than theta d, T when T is very less than theta d. Generally in this region it is 1/10 of theta d generally is considered. So, it follows this. So, upper half here when theta d is T is greater than theta d. So, it is so now what about in between these two? So, one has to basically integrate of this one. So, this is the energy, basically, this is the energy. Okay. So, this is the energy. So, one has to integrate, but I will not integrate. So, that is your homework. Okay. So, it generally after you integrate you will get CV for this region or in general for whole without considering high temperature, low temperature, this limit. So, in general this comes, and it is difficult to integrate just like this analytically. So, generally we take help of, so we can do numerical calculation. Okay. Analytical calculation is difficult, but this form CV, this form general form CV, in general CV equal to del E by del T at constant V. So, this is our in general things, and that generally it comes 3, I can write like this 3 or okay, then 3. So, CV generally it comes that 3 or 3. So, this then it comes like this. So, you see this is, so this contains also x T, right, h nu by k b T, and outside also T is there. So, it is just if you differentiate this one. So, this comes just I am writing the result. I will not do that, but please you can try to do that. So, it comes generally yes, general behavior, it generally write this. So, 3R, so from here 3R, so rest of the part depends on T, depends on 3. So, this write Fermi, that not Fermi, that Dirac function, Debye function, sorry, Debye function, which is a function of T, or I think this one function of theta d by T. Okay. So, this CV is basically 3R and the Dirac function, Debye function, and Debye function at lower temperature, higher temperature limit it becomes 1, okay, and lower temperature limit you can see it will be in this form. Okay. So, what is that form of this Debye function phi d? So, that just I will write it. So, 3 T by theta d cube. Okay. So, it is the 3 T by theta d cube, okay, and then integration will be there 0 to theta d by T, theta d by T, theta d by T, right. our xd was theta d by t, xd theta d by t, and then x part was there, so it's the differentiating, so it comes really x to the power 4 e to the power x divided by e to the power x minus 1 whole square, okay, and then dx. Okay. So, these are called the Debye function, and that for CV, that is for CV, and one has to find out this, that is the general form of the integration, and so it's difficult to integrate it analytically. So, to get this whole curve, one has to take numerical value, numerically one can do it. Okay. It's maybe computing through computer programming, writing programming through taking help of computer. So, one can generate points, one can generate points in this range basically. So, for higher temperature, lower temperature, one can take the limit and find out, but this will give, just if you numerically if you do this, just taking help of computer, it is called numerical calculation, not analytical calculation, while analytical is not possible. So, that is the advantage of doing the numerical calculation, taking help of computer programming. Okay. So, I think that is the history of this, CV, specific heat of solid state. Okay. So, development of this theory, starting from Dulong-Petit to Einstein theory, then Debye theory, it's only difference. You see the difference of the taking realistic model, okay, taking realistic model and including the quantum phenomena. Dulong-Petit completely it was classical, then Einstein considered it the quantum oscillator having quantized energy level, okay, and but he considered this only one frequency in all atoms are oscillating independently. Okay. So, that is not realistic assumption. Okay. So, for any theoretical calculation we take model, we have to assume it, because taking just real system it is difficult to calculate, difficult to do analytical calculation. So, that is why one has to assume some, one has to assume, okay, some points, one has to consider some, one has to simplify the system, okay, assuming or some, it is called hypothesis or postulates. Okay. So, which has no direct proof, but if I consider some assumptions, some postulates, some hypothesis, then based on that if I develop a theory, and if that theory fit my experimental result, then we tell that this model is correct. So, this model is close to physical model, close to system. So, system behave like this model. Okay. So, that is the very important, and does this theory develop with time. Okay. So, that finally Debye could explain nicely, but there are still some deviation of Debye theory, okay, for especially for low wavelength, elastic wave of low wavelength. When wavelength is low, then it can see the atoms. Okay. So, it will not see the solid as a continuum medium, it will see the discreteness, it will see the atoms are arranged. So, that for that basically one again has to calculate using that discreteness of the solids, and that can be done nowadays. That way only we deal with the system, but I will not go into that. So, now what I want to tell you, the lattice vibration always we tell nowadays in terms of phonon vibration. Lattice vibration is nothing but the phonon, oscillation of phonons. Okay. So, lattice vibration is expressed in terms of phonon. Elastic means, lattice vibration means that gives the elastic waves, or elastic wave propagates through the solid, and then it vibrates the then solid vibrates, okay, as a whole it vibrates, okay, vice versa. Now, this elastic wave, it can be expressed in terms of phonon. Okay. So, that is just similar concept of photon. What is photon? That you know, this light, that is a photoelectric effect, right. So, light wave, electromagnetic wave, light wave is electromagnetic wave. Light wave is electromagnetic wave. So, I will give some preliminary concept of phonon. Okay. It is equivalent to photon. So, photon in case of electromagnetic wave, and the similar way this phonon is basically the in case of elastic wave. Okay. That is the difference. So, basically this photon or phonon, that is basically the quantization of the wave, okay. Quantization of the wave, or quantization of the energy of the wave, right. So, that is the photon or phonon. In case of quantization of the electromagnetic wave, that is photon, and in case of quantization of the elastic wave, then it is phonon. So, basically energy of a vibration, of a lattice vibration, energy of the lattice vibration, what is that? Energy of the lattice vibration. So, lattice vibration is expressed in terms of mode of vibration. So, each mode of vibration having particular frequency, right. Each mode of vibration is having particular frequency. Okay. So, phonon is defined as the quantization of the lattice vibration, is defined as the energy, quantization of the energy of the lattice vibration, means quantization of the energy of the elastic wave, right. Because this mode of vibration, lattice vibration in defined mode. So, mode of vibration is nothing but the elastic wave. Each mode is a one wave having different frequency and wavelength, right. So, then I can tell lattice vibration or elastic wave or mode of vibration, they are quantized in lattice, right. So, this the quantization of this lattice vibration in terms of mode of vibration, right. They are basically quantized, and each quantum of a particular energy, quantized. So, each quantum of a particular energy, so that is h nu, smallest quantum energy, that is h nu, that is the phonon. That means, a mode of vibration or an elastic wave is made of phonons, an electromagnetic wave is made of photons, means one electromagnetic wave may not be one photon. So, it can have a number of photons. So, few number of photons together gives a electromagnetic wave. Similarly, few number of phonons gives a elastic wave, gives a mode of vibration. Okay. So, now as I told you that each mode have a particular frequency, and that corresponding to that frequency there is a energy h nu, right. Now, in ground state its energy may be h nu, because its frequency cannot be changed h nu, but when it is thermally excited due to external excitation, that mode it can go at higher energy level. So, that higher energy level, as I told, is like harmonic oscillator. Okay. It has h nu, 2 h nu, 3 h nu, n h nu. Okay. Okay. So, when when this elastic wave or mode of vibration is in nth energy level, okay, so its energy of that mode in ground state it was h nu, in excited state, okay, it nth energy level, when it is excited to nth energy level, so its energy is n h nu, its energy is n h nu. Okay. So, then we tell that this excited mode of vibration or this elastic wave, it consists of n number of phonons, Okay. So, in crystal vibration, lattice vibration, we have seen 3n number of modes. So, 3n number of frequencies are there. For each mode, if it has ground state energy, its smallest energy in terms of this quantity h nu 1, h nu 2, h nu 3, h nu 4, right, h nu 4. Right. So, these are the energy of each of different mode having different frequency, right. And now, each of this mode, it is a lowest energy, it has own energy, higher energy levels like harmonic oscillator, okay. It has higher energy level. So, it can stay, when it is excited, so it can go in any other higher energy level, okay, of its own energy level. So, these are in terms of this will be 2 h nu 4, but in this case 2 h nu 1. Okay. So, it has own energy, higher energy levels, Okay. So, this at ground state. So, for each mode have its at ground state. So, as a whole this whole wave, elastic wave, we can consider when it is ground state, we can consider its one phonon. It consists of one phonon. When it is at higher energy level, nth energy level, so it contains n number of phonons. This also n number of phonons. This also at higher state n number of phonons. Okay. So, each mode can have any number of phonons. So, number of phonons it tells the excited state. Okay. So, at ground state each mode of vibration, lattice vibration equivalent to elastic wave, okay, is a phonon. It has 3 n number of types, 3 number this 3 n number of types of phonon. Type means this phonon at ground state this 3 n number of modes are there. So, that we can tell that 3 n number of phonons are there, all of them having the smallest energy, the quantization of the energy. Okay. So, smallest energy h nu 1, h nu 2, h nu 3, h nu 4, etc. Okay. But each wave or mode of vibration, okay, it can consist of few number of phonons when it is in excited state. When it is in second energy level, so 2 h nu 1 or 2 h nu 2, etc. Okay. So, it consists of 2 phonons, 3 phonons, 4 phonons, n number of phonons. Okay. So, now as a whole my system, that crystal vibration, now I can tell that this I have this is nothing but a system of phonons. Okay. So, phonons are having this h nu 1 energy, 2 h nu 1 energy, 3 h nu 1 energy, right, as each mode can have this different energy when it is excited. Okay. And this another phonon for another mode. Okay. So, this h nu 2, h nu 2 h nu 2, 3 h nu 2, etc. Okay. So, depends. So, the all mode are in ground state, that means the system is having 3 n number of phonons having the lowest energy. Okay. So, each wave, elastic wave is 1 phonon, okay. But each phonon have probability to go in any excited state, and that excited state it expressed in terms of some number having the same quantization of the energy, either h nu 1 or h nu 2 or h nu 3, whatever. So, this lattice vibration is, that is why considered it is a system of phonons. So, I think that is much I could tell you, just to give you the idea of phonons. So, whenever there is scattering from the lattice vibration, that we just tell scattering between electron and phonon, scattering between electron and lattice. So, that we tell scattering of electron and phonon. Okay. So, I will stop here. Thank you for your kind attention.